The point of this talk it's also that quantum key distribution is not a technology that's ready right now, and not a technology that will ever replace cryptography. But the point of this talk really is to show how quantum key distribution can be a part of cryptography, how we can actually improve security by using quantum QKD, even right now, even if we don't have these fancy things like information theoretic security. There is a place for it, we just need to figure out which it is. And we need to stay honest about that. Oh, and if you want to follow the talk, feel free to look at the slides, they're online. They're on GitHub. If you want to follow along, there's a bunch of stuff where you might want to look at more deeply for some time. We also post all our talks on rosenpass.eu, so you can keep up to date on that. So why am I here? Why am I talking about this subject? I am the main author of Rosenpass. Rosenpass is a post-quantum secure key exchange, and it's used to secure WireGuard against quantum attacks. It is a real-world cryptographic application that you can use right now that's actually deployed by quite a few people, that's used by companies. So that's where I'm coming from. I'm kind of the person who's going to trying to tell you what it would take for me to want to use QKD within the context of a protocol like Rosenpass that's actually being used. And finally, this is what we are, or this is what we are trying to become, an organization for translation research. I think there needs to be more communication across disciplines in these topics, and there needs to be more communication looking at all the parts of the cryptographic workflow, and that's what we're trying to do. Okay, so let's start with a bit of an introduction about cryptology. On this slide, you see, okay, so I have a professional scientific illustrator, and this is what comes out if she's stuck in Deutsche Bahn and doesn't have time to do anything. You get to see my templates that I give to her to produce something proper. It still can illustrate the point I'm trying to make a bit. Cryptography isn't just one discipline, at least if you're doing real-world cryptography that's actually supposed to secure systems. Cryptography is a feedback loop of many different disciplines. So how do you develop a cryptographic system? You kind of start by figuring out, informally, what does security mean? What am I trying to achieve with my security? That is a philosophical type of engagement. You're trying to figure out what does security really mean in a context. Then we go into mathematics. We need to operationalize our philosophical definition of security. We need to figure out, can I put all that stuff our philosophers or socially minded people have thought up about security, can we put that into math? Next, we develop a mathematical construction. Something that can hold up to that definition of security and something that can be proven to fit that definition of security. We continue to implement it. That's computer science. And now, in my opinion, a step that is crucial, but a step that is often omitted, is you actually need to close that feedback loop. You actually need to have social science and empirical science looking at the systems you built and look at, are they actually secure when put into a human context? Do people get what the system is supposed to do? Cryptography is supposed to create trust. Does it actually do that in practice? So the cycle closes itself, and then within each cycle, of course, you have internal review cycles. You build something, other people try to attack it, write a paper about it, and in the process of attacking your work, improve it. One final aspect I want to mention about this, as you can see, there's these many different disciplines involved, and with each step within that great circle of feedback, there's some loss of fidelity. When you take a philosophical definition and put it in mathematical terms, that might not have been correct. You might have been attempting to reach that philosophical definition, but you might not have managed to. When you're implementing an abstract mathematical algorithm on real hardware, you might not have successfully done so. you might have a bug in your code that needs to be fixed. So cryptography, real-world cryptography especially, is about keeping track of these transitions, keeping track of the loss of fidelity that happens when you go from one discipline to another. The reason why cryptography, despite this big loop that's involved, is still very effective at doing what it does. Cryptography is extremely secure mathematical cryptography. The reason for this is because on the mathematical side, back there where there's mathematical operationalization and mathematical algorithms, people write proofs about their cryptographic algorithms. It's actually an advantage that we model these algorithms in mathematical terms because we can now mathematically prove statements like, is my algorithm actually secure? There's two ways this is done. Two broad ways. There's many ways, of course, but the broad ways are reduction proofs and information theoretic proofs. And what you're doing, if you're doing a reduction proof, you're trying to take some other system that exists, for instance, a mathematical problem or another cryptographic system, and derive a statement saying, if this well-established system is secure or hard to break, my system is also secure and hard to break. Taking RSA for an example. To prove that RSA is secure, what you might do is assume there exists an attacker against RSA and use that to solve prime factorization. And what you've now just done is you've basically done an argument from absurdity to show that breaking RSA should be at least as hard as factorizing prime numbers. Now, of course, the underlying mathematical problem, prime factorization, we don't know if that's like actually secure. That's why you have things like quantum computers breaking these assumptions. But a lot of people have looked at prime factorization for a very long time, and nobody has found an attack. So we're not constantly introducing new mathematical assumptions. We actually keep relying on the same ones over and over and over again and keep focusing on a very limited set of assumptions that really ought to be secure. The second one, and that is important for us today because that affects QKD. The second one is information theoretical security. And in a nutshell, what you're doing when you're targeting information theoretic security, you kind of model your cryptographic system in terms of a function that takes a key material value that is kept secret by assumption. You take some information to be protected, and you output some information that is leaked. The information that is leaked is known to the attacker. And then what you do is basically you derive a mathematical statement saying, for every value of my leaked information, each possible value of the protected information is equally plausible. Usually that means you just have a key that's as long as the protected information. And that's how a one-time pad works, which is actually used in QKD. This is generally what is done to show these systems are secure. That's done in more places than QKD. There are other parts of mathematical cryptography actually that provide information theoretic security, usually as part of a system, and then you need to get that key material somewhere, and then computational assumptions of security come in again. But this is basically what you do if you attack a system like that. If you perform a brute force attack against a inefficient to solve problem, you usually get a few candidate plaintexts. If you perform a brute force attack against an information theoretically secure system, you produce all possible plaintexts. So brute force doesn't help you at all. There is more ways to use proofs in cryptography. There's actually quite a few ways to use proofs in the informatics side of things. You might need to show that your implementation of an algorithm is timing side channel secure, because if depending on different secret inputs, the time behavior of your algorithm is different. That might leak your key. So people started to develop methodologies to ensure that doesn't happen. And there's a lot of this stuff happening in the implementation side of cryptography. There's actually a lot of math side there too that actually checks, are our implementation secure? Because you need to guard even against things like, hey, the electricity you consume, the amount of electricity you consume. If you graph that, or just put a camera to an LED, that is your power LED, you might be able to extract keys. All of these are things that are studied by cryptography and much more. So this is something our Science Illustrator actually did a while ago, which is why I like it very much. Cryptography is a social discipline. It's an interdisciplinary discipline. You cannot do cryptography without interfacing a lot with other people. If you don't, your system is going to be insecure. If you keep details about the cryptographic system you've built, you've designed secure. Essentially, what you're doing is you're breaking that entire feedback cycle that I showed you beforehand. And you're not allowing people to actually attack your system. And it's probably going to be insecure. Experience shows that if you don't stick to that feedback cycle, your system is going to be insecure. But if you do, people are also going to find bugs. People found bugs in Rosenpass, minor ones, but they still found potentially security impacting flaws that could threaten uptime of the system and things like that. And they're going to report them and they're going to be improving your system. So don't think as cryptographic attacks as something that's like breaking your system. Think of these as scientific friends who are trying to turn your system into the best possible system there is. That is simply part of the process. So what should quantum key distribution or similar disciplines actually that try to provide security on a hardware level, I think that's relevant for radio, 5G, 6G based security too. These researchers should integrate with the cryptographic community. It's already interdisciplinary. We might as well add another discipline. However, open science approaches must be used. If everything's secret, this entire feedback cycle won't work. And please use security terms from cryptography. If a cryptographer can't read your paper because you use entirely new definitions, first of all, your definitions are probably not going to be super sound because you've spent less time doing them. Good job, but we've had 50 years of research on security notions in cryptography. So please use them and allow researchers to actually look at your stuff and do this quick check during peer review. And finally, use quantum key distribution or another hardware-based security measure within your system instead of using it as an alternative. So the field we're actually talking about here isn't key exchanges. Quantum key distribution, these types of technologies always tend to focus on the key exchange, but actually what we're trying to create is not a secure key exchange. We're trying to create a secure communication channel, which is why the field is called secure channels. Examples of secure channels. You're using secure channels right now with the device in your phone. The most frequently used type of secure channel is TLS, but there are others. For instance, there's OpenSSH, which you might be using if you are administrating a server. These systems are cheap, fast, secure, well analyzed and authenticated. And this is an image of the TLS certificate used on the Rosenpass website. This stuff is ubiquitous. It is one issue though. It's not right now super secure against quantum attacks, but you can fix that, for instance, by using my stuff. So here's an advertisement block. Use something like Rosenpass, or actually use OpenSSH or the Signal messenger if you're chatting with each other, because Signal started to introduce post-quantum secure aspects of its cryptographic algorithm, so did OpenSSH. Rosenpass does it in a very comprehensive way. OpenSSH and Signal are doing it in a more incremental way, but that's all right because these protocols are deployed on billions of devices. So you kind of want to find the right trade-offs. These people are doing excellent work. i.e., post-quantum security is practical right now based on mathematical assumptions. So let's provide a bit more information about cryptography here. Let's talk about security properties because these are important in order to be able to converse here. Basic definition, passive security, somebody who's trying to eavesdrop on your communication. By the way, our scientific artist is also a comic artist, which is great if you're trying to show basic stuff. Active attackers are intercepting your communication. That is a man-in-the-middle attack. This is a basic distinction used in cryptography, and if you create something that is passively secure, cryptographers are going to look at it and say, that's kind of nice. We kind of want active security. This has been the standard since 1995. Security properties themselves. Now, what we had before were categories of security properties. Now we have just security properties themselves. We want secrecy. Don't leak the data you're transmitting. That's the most basic property. Don't think I need to elaborate much on that. We have authentication. This is one that's usually omitted when talking about quantum key distribution or similar technologies, although it's a vital one. If you don't know who you're talking to, you're going to get a man-in-the-middle attack. So any cryptographic system, in order to be considered secure, must provide authenticity. It must tell you who is this from, and it must tell you in a secure, provable way who this is from. There's identity hiding. People notice that if you're chatting on your mobile phone with somebody and using cryptology, you kind of don't want to have a setting where everything you're saying could be shown to a court and they would know, yes, that's from Alice. So cryptography should provide this security property called plausible deniability in general, where you can't really be cryptographically pinned down on what you said. Informal communication channels in practice are very important. It's one of those social findings, essentially. There's deniability. Oh, sorry, I got it wrong. Identity hiding is the one where you don't know from the data you're cryptographically transmitting who's talking to whom. It's a form of anonymity. There are stronger forms of that in real life systems, like, for instance, Signal, where not even Signal knows who's talking to whom. Identity hiding just refers to the protocol, to the secure channel not leaking that information. And here, deniability. Here we have that deniable channel, this informal channel. Sometimes you might not want an informal channel. Sometimes you want a formal channel. If you're sending information from aircraft to aircraft or from aircraft to ground station, maybe you actually want to have a proof that everything that was transmitted like this. Which is why you might also have non-repudiation. This is something the designer of a system just needs to decide upon. Which of these properties do I need? And now it gets interesting, because now we're approaching the part where we're actually talking about quantum key distribution, because there's forward secrecy. Forward secrecy protects you against somebody breaking into your server, stealing your secret keys, and being retroactively able to decrypt your past communication based on the ciphertext. Of course, if you start plaintext, that won't help. That is straightforwardly done by using an extra asymmetric k-pair and then erasing it right after usage. It's called forward secrecy. It's not secure against interception. It's a passive security property. Passive security properties are still useful, though, but it's used in addition to security properties like authenticity. And it's not secure against flaws, future attacks in the asymmetric cryptography algorithms themselves. Or actually, it's not secure against future flaws in the symmetric cryptography algorithms. It would be nice if we could even break against these sorts of flaws, and this is where QKD could come in. If you had information theoretic security and you used it as part of a cryptographic system, what you could get is everlasting secrecy. Everlasting secrecy basically makes sure if there was no man-in-the-middle attack, during the communication itself. And if the QKD system is secure, it can't be decrypted in the future. That's why it's called everlasting secrecy. Still not secure against active attacks, though. So if somebody comes and just does a man-in-the-middle attack, everlasting secrecy won't help you, which is the basic reason why you'll always need mathematical cryptography. As long as you can't defend against man-in-the-middle attacks, you should be including cryptography in your system. And even if you can, you probably still should be including mathematical cryptography. The colors are not super easy to see here, but this is a comparison between quantum key distribution and software cryptography. As you can see, on the side of QKD, there's a lot of reds, tiny bit of green, and quite a bit of yellow. Red is bad, yellow is nice, or okay, and green is nice. Whereas on the software encryption side, there's one red part, and everything else is green. So software encryption provides the basis of security. It provides these features like security against active attackers, end-to-end encryption. It provides identity hiding, non-repudiation if you want it. It provides deniability. It provides all these nice things. What it doesn't provide is everlasting secrecy, because it can't. You can't rely on mathematical assumptions there. You need information theoretic security to get everlasting secrecy, and quantum key distribution could provide that, but oh damn, quantum key distribution is impractical. If you want to provide everlasting secrecy, you're stuck with a few, I don't know, you can tell me bits per second. End-to-end security for quantum key distribution is also impractical. If I properly want everlasting secrecy, I need to have a QKD device on my phone. And the person I'm talking to also needs a QKD device on their phone. And the quantum information needs to be transmitted via radio and then go through all these fiber channels or copper lines through the entire internet back to the other party. If you can't do that, it's not end-to-end, it's nice. Well done. It's not the standard we set in cryptography. Where do we go from here? We want to use QKD, right? This is why we're here at this talk. We've already set our minds on the methodology. So we need to come up with a reason why we would be using that methodology, as is often done. We need to redefine success of QKD. Paul, who's sitting over there, who's giving a talk later, and I are working on a paper on that topic. So we spent a lot of time thinking about why would we want to do that. And there's actually some reasons why you might want to use quantum key distribution. Symmetric cryptography is considered very secure. We've been trusting that for 20, 30 years. We trust asymmetric cryptography a bit less. This is these two pillars. We trust classic asymmetric cryptography a bit less because it's not being deployed as long as the symmetric part. And there's this thing with quantum computers that might break it. And we trust PQC a bit less because it's been standardized a month ago. So we kind of want to wait 20 years before we really put a lot of trust in that. In comes quantum key distribution, which might actually provide a bit more redundancy. You're not going to secure your symmetric cryptography using QKD. You can't, because you want some measure of performance here. But if you exchange keys with QKD and feed it into a symmetric encryption algorithm along with classical and post-quantum key distribution key material, this actually provides some value. The scenario you're guarding against here is, think 10 years down the road, somebody builds a quantum computer and somebody, goddamn, built an attack against the established post-quantum cryptography schemes you've been using for 10 years. If those two things happen, it's not super likely that they will, then if you use quantum key distribution right now to secure your systems, you've actually added value. Of course, if the symmetric cryptography algorithms are broken, you're lost. But let's hope they won't be broken. What I've also done is started to view QKD as a form of enhanced hardware security. If you're the type of person who would build a wall around their fibers, you might as well use QKD, do it a bit more cheaply, but be more comprehensive in other places. So if you start thinking of it not as this alternative to encryption, but as an adjunct, as is hardware security, putting guards around your fiber, if you want the highest possible security, actually is quite a good idea. It does create real security. If you think of that, QKD has a place. This is the key message. What comes now is, again, advertisement. In the talk after the next talk, Paul is going to talk about that concept of using quantum key distribution. These blue stuff here, this is actually one I drew myself. I'm very proud of that. My scientific illustrator really didn't have much time. But you have these blue quantum key distribution nodes, and then the end-to-end yellow dotted line called quantum, a post-quantum classical end-to-end cryptographic computational encryption system is going all the way from Alice to Bob. You put those things on top of that, and then you use some standard technologies on these routers to bring the cost down and not to have to buy 500 different QKD devices, but maybe one per node. And then you have the fantastic concept Paul has come up with, but he's going to tell you about that in a while. I am just going to leave you with that slide. This is the core takeaway about why you might want to use QKD. Besides the takeaway about, hey, integrate with the cryptographic community, use cryptographic terms. These are the things I want you to take with yourselves. I don't like to hear, when I read papers, I don't like to hear, hey, post-quantum security has limited trust from industry or something like that. All the justifications I see in QKD papers, but also in PQC papers actually, tend to be a bit harebrained. Actually look at the scenarios in which it would help me. Cryptography is not about adding security. You can't create more security, but you can create more scenarios in which your system is secure. And a second layer of encryption never does anything but looking at another attack scenario that you can guard against, that is real value add to cryptography, to security. So think of it like this, covering more cases. Thank you very much.
Thanks for your fine presentation.
I can start. Do you have an expectation? So QKD is very expensive. Do you think you can ever use it? So do you have an expectation when this will be the case, when you have this nice scheme, what you have, where we will have heard some more? Do you have some idea?
So I think it's about usage area, right? I think like the system that I've shown here, that is something that maybe an embassy would use, or somebody who really is already spending a lot of money to secure the encryption. I wouldn't expect to see that ever on my mobile phone, but maybe I will, and then it's going to happen when fusion is happening.
I have another question. So you given a very nice overview on security things and security measures. Perhaps what I missed a little bit is what Bulas is doing also. It's covered communication. So you missed the part. Perhaps sometimes someone only want to know if parties are communicating or not. I think that was not in the list. Or if you...
Let me go to the bonus slides. So I had a part in the talk about cool things you can do with cryptography right here that are not about encryption. For instance, you can do censorship circumvention. You can have technologies like Tor, where you use onion routing to make sure people can't even observe what you're doing. There's some cool research on mixed nets to provide anonymity and to provide communication security. There's a ton of areas in cryptography that aren't covered by encryption. This is one of the other reasons why cryptography will prevail. We can do a ton of things, and most of those I don't know anything about. But hey, people can do multi-party computation where you can run a empirical study with people's medical data. Nobody knows what that input data is, but you know the computation is correct, and you know that nobody cheated during the computation and everybody just gets the result. These are magical results that cryptography can provide. And actually multi-party computation I've learned that recently, provides information theoretic security, I think with some bootstrapping. So cryptography is a magical place. It can do a ton of things. Some bad ones, like Bitcoin, wouldn't have happened without cryptography, but maybe something good will come out of even that.
So I had one question regarding the part of hardware security. So is this an empirical discipline, or do they also provide proofs which are based on physics, physical laws like Maxwell equations or so?
So hardware security. We're in, let's see if I can get there. Maybe I can't. So we're in kind of this part here and this part, where you're looking at the security of implementations on real-world hardware. There are methodologies that are used to provide proofs there. Let's see if I had it here. No, I didn't. It's in the bonus slides. I'm not going all the way back, but actually you can create, so for instance, with timing side channels, where you're leaking key information through the timing behavior of your algorithm, actually we have some knowledge about how to prevent that, because certain CPU instructions do leak timing information, like branches, for instance, whereas others don't. So there's this branch of constant time cryptography. And we have formal ways to study that. For Tempest, for side channel attacks that are not timing side channels, it's much more fuzzy. It's a very empirical discipline. It's also a treasure trove. People are writing papers on like, hey, let's attack the system, and they find, yeah, we can. It happens all the time. So it's not as nicely formal as something like timing side channel resistance. And I think this is an area where something like QKD could actually add something. That said, what it really comes down to is the willingness of hardware manufacturers to actually implement secure systems. We're kind of at the state right now where hardware manufacturers have no interest at all in actually implementing systems that provide secure cryptography. There are some people who are trying to do better on that. There's a project called OpenTitan, which is about implementing a custom CPU that is actually special purpose made for cryptography, but as long as Intel specifically tries to prevent cryptographers from writing secure implementations, I don't think we have to go down to Maxwell laws. But all these problems are actually going to be problems for QKD as well. The security of QKD in practice. There have been papers on side channel attacks against quantum key distribution. So you might have theoretical proofs of security there, but I want to see the empirical proofs too. You can't just do, if you just have the theoretical formalizations, the ones that you use in practice might not hold. Your model of the real world might not be good. So this is where we really need this empirical approach, and this is where QKD devices need to be open before I can trust them.
So thank you for a very enlightening talk, and I will check out this Rosenpass thingy. However, I'm kind of I don't want to say taken aback. One of the reasons why there haven't been many empirical studies of QKD, and by the way, I am the last person to defend QKD in this crowd. I am from US. We are basically pretty much forbidden by our funding agencies in doing anything QKD related. I'm sure you've seen that little page that National Security Agency
Can I just say at this point, you're allowed to be taken aback because I was intentionally being provocative.
That's fine.
So,
well, then thank you for being open to this. Then, QKD by itself does have empirical studies of security. The problem is that those systems aren't as widespread as the encryption that we use pretty much every day on every one of our devices. I mean, heck, that little owl thing over there that is a camera that creates makes the Zoom call possible, that has more computational power than probably the entire United States Apollo program that launched the man to the moon, and most certainly has encryption in it. So
because the Apollo program had very little computational power. They had to use special circuits, and my mobile phone also. This
yes,
thing probably has also more computational power.
yes, but so there's kind of this vast, there's vastly more opportunities for people to do empirical studies of the standard security. So to compare that is like comparing, apples to rabbits. It's a completely different beast. That being said, I agree with you. I think that we need both. My question to you.
Can I just interject here and just reply to these theses real quick? First of all, I agree with you. Like, first of all, I was intentionally being provocative a bit. And of course, there are more cryptography deployments there. That said, I think what I'm targeting here is not necessarily saying, hey, you guys, you researchers are doing a bad job at empirical study. I think for me, this open source, open science approach is more important. And I can't really, like I'm a cryptographer. Most cryptographers look at quantum key distribution with these tired, benevolent eyes that you might give to a 16-year-old first time in love. I don't quite look at it like this. I think there's real value in quantum key distribution here. I think there's also a hype. I think there's real value in blockchain. I think there's also a hype. I think it's a matter of taking these things apart. And there's a matter of, there's a matter of taking these things apart, and there's this openness. It's really what I'm asking from manufacturers and not necessarily from researchers.
And actually, I really appreciate this perspective. You're probably the first cryptographer, if you can call yourself that I've ever met who actually learned about QKD before criticizing it, which is very nice.
Okay, there's one question from Karim from Zoom. So he wrote, can you point out, please, to the post-quantum VPN software, and how would you put it within the diagram of cryptography that you showed earlier?
So I don't know what is meant with point out. I can mention the name again. It's called Rosenpass. It's Rosenpass for WireGuard. Makes quite a nice image, I think. It fits in everywhere in this discipline. So we have aspects of our work that are actually novel cryptographic work. We don't have so many new operationalizations of security. We don't, but actually we do. So like we cover like the entire engineering spectrum and mathematical spectrum there. The empirical spectrum, we are looking at that, how to do that. That's really not my personal cup of tea. So I'm looking for collaborators and maybe some funding to make that happen, and people who want to kind of like have the hat for that. But really, I think for a project to actually be successful, it needs to cover the entire range of methodology. Yes, it is. It is open source. You can download it right now and use it right now.